and welcome to episode number 12 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, we are going to start a new topic, and that is the topic of virtual memory. If you're following along with the textbook, my recommendations for reading, and again, it's not required, is to look into address spaces, address translation, and segmentation. The other comment that I wanted to pass on to you is that you should look at starting assignment 2 as early as possible. Now, I know most of you have just come off of assignment 1 and you might be catching up in other courses. The deal with assignment 2 is that it doesn't take that long to write the code for. The problem, of course, with assignment 2 is that it takes a really long time to debug it. So if you've made a little mistake, it's actually really, really hard to find the error and get it cleaned up. To help you out with debugging assignment 2, I have made a Piazza post about common OS 161 errors. It especially deals with any of the memory errors, like TLB misses, and it also deals with some of the more common errors from wide fork and fork test and some of those things like that. So just some things to think about when you're actually trying to test assignment 2. Please make sure that you read that post when you get an error before you post a Piazza, because these are the most common errors that we actually encounter. All right, so let's move over to our OS of the day then. And today we are dealing with BSD, or Berkeley Software Distribution. Now, this was released in 1978. It's a product of Berkeley, and it was released originally for the PDP-11, which is from Digital Corporation, which I think has been bought up by HP now. So what's interesting about BSD, and I mean BSD is something that probably most of you have used, but didn't realize it, or you've used something that is derived from BSD. BSD actually did not start out as its own operating system. My understanding is it actually started out as a bunch of extensions for the 6th version of Unix. And they called it 1BSD and 2BSD. And this is actually where they created some educational Pascal software. Now, Pascal is a language, and many of you may be familiar with it, and some of you may not be. I want to say before C became super, super popular, if you were to go through like the Toronto Stars, like want ads, Pascal was super popular for want ads in like the late 80s, early 90s. And it wasn't, I want to say, until the mid 90s, late 90s that you actually see a lot more C requests, which is kind of interesting because C had actually been around for longer than that. But yeah, Pascal is a C-like language. It also had an editor, a shell, and a bunch of new shell commands, and even a game in it. So there's some add-ons to Unix to make it, more usable and more friendly and things. And then in 2BSD, we see two things that most of you have touched. One is VI, and the other is the C shell. Not, of course, to be confused with C shell, that thing you used in CS136. I mean CSH, the real C shell. Now, it was after seeing the popularity of those, they actually went out and they realized they wanted to make their own operating system. So 3BSD was actually a full-blown operating system. It was going to be called a VM Unix because one of the things that they wanted to offer was an implementation of virtual memory for VAX machines. And it was highly successful. It got DARPA funding. It's the first Unix-like operating systems that had IP stacks. It had sockets and all of those lovely things to make networks and internet networking work better at the time. Now, you might be like, wait, they had internet in like 78? Yes, they did actually. The internet as you know it, being a web browser where you type a URL, that really only became popular in about 93, 94. And with like the release of Netscape Navigator. And before then, like in the 80s, you could absolutely connect to the internet. It just wasn't what you're expecting. It was more like messaging boards and emails and things like that. It wasn't like, welcome to the Star Wars website. No, it's nothing like that. There was no YouTube. So yeah, BSD actually was super successful, and obviously it is still around, and there's so many different variations of it that we couldn't name them all, but there's things like OpenBSD and FreeBSD and NetBSD, and there's a lot. And then there's all the operating systems which are closed source but are based off of BSD as well. For example, SunOS, also known as Solaris in later years, but also one that I'm going to estimate that 40% of you are currently using some form of right now, and that is macOS. Mac OS X is a BSD variant. Heavily modified, obviously, but it still stems from BSD, which is kind of cool. Sometimes it's kind of cool. All right, so that's BSD. So let's dive into our topic today. And to do that, I think I'm going to start up OneNote, because that seems smart to do. So what we're going to talk about today is virtual memory. So this is a new module. Again, all of these modules are actually posted on, there we go. So these are all actually posted on the course website. So this is our biggest section of the course, and that's talking about the abstraction that we perform to for RAM. And before I get into this slide here, I want to talk to you more about where this is all coming from. So the first thing we should talk about is what's an address space. Now this is something that if you took CS136, which in order to be in this course, of course, you had to take CS136, you would have learned a bit about address spaces and address space layouts. And you know that every program has an address space, and the address space has a particular layout. Now that layout is actually dependent on both the operating system and the compiler. They are going to, the operating system is going to dictate what the address space has to look like, and the compiler is going to make sure that that's how it actually works out. So if we look at the address space for a program, I've really got to glue this tiny piece back onto my pen because it keeps falling off, and I don't know why. So if you were to look at an actual address space, so this is our address space. And in CS136, they would have told you there are a bunch of regions in this address space. So you know that there would be a code segment. And you also know, or you might remember, that the code segment lives at the lower addresses. So this is address 0, and this is, well, let's say this is the following, which isn't quite accurate, and we'll fill in all the details to this later. So, you've got code, and then there would be things like your constants, your global constants, and then you'd have your global variables and your heap and things like that. In this course, we only use 3 regions in our address space. So we're going to have code, which is going to actually include the read-only memory. So any kind of global variables that would be read-only, they're actually going to live in our code segment because our code segment is also read-only. Different operating system, different rules. We also then have a data segment. And then the last segment that we worry about is the stack. And and hopefully remember from CS136, that the stack lives at the opposite end of the address space. A part of the reason for this is because if you have a heap, and we don't have a heap for user programs, but if you had a heap, the heap needs the ability to grow, and the stack also needs the ability to grow. And since they're growing into the same region, you want to give them the most space possible so they can grow, so you put them really far apart. Now, the truth is, in operating systems, this has a fixed size. That is a maximum size. And there are system calls that you can use to increase the heap and increase the stack, but you don't have to use them. But there is a maximum size that they will actually allow the stack to be. In OS 161, the maximum size of the stack is actually going to be 48 kilobytes. It's not a lot of space, but think about it. You're not really doing anything with this operating system. We don't need a bigger stack. And if you're looking at any kind of Linux kernel-based operating system, Mac OS, or Windows, you're looking at a default maximum stack size of usually between 1 and 2 megabytes. And you can actually write a fairly simple program to actually prove that there's a fixed size. And all you have to do is make a really big structure. Now you may, well, how do I do that? Well, you make a structure that contains really big 2-dimensional arrays. And then make like an array of those structures. And you'll see that, and you make it make the array of structures bigger and bigger and bigger, and you'll see that there's a cap, and you can actually compute exactly how big your stack is, and that's kind of neat. So this is our address space. Now what's interesting is you'll note that the addresses for each address space appear to be the same range. So if this is the address space for MATLAB, then, and let's say we were running a different program at the same time, there is another program here, code, data, stack. This would be the address space for another program, and let's say this program is OBS, which is the tool I'm using to stream live to you right now. So here's the interesting thing. You'll note that the range of addresses used for both of these address space is actually the same. But that would give us the implication that this code segment is magically overlapping with this code segment, and that this data segment is overlapping with this data segment, and my stack is colliding with this stack. So that's maybe not making that much sense. So the next thing you might think of is, well, what if it was like, here's MATLAB's code and then here's OBS's code. So maybe they are alternating places in the address space. No, they're not actually. Let me show you one more thing of what I mean. So I have a couple terminals here open, and I'm going to open this a little piece of code, if I can remember which file it's in. I think it is sample1. Yes, sample1. That's the right one. So yes, I'm aware this is C++ code, and in this course we tend to use C, but I prefer C++. You can prefer whatever you like. I prefer C++ to C. So here you've got our includes and all of that. Now you'll see at the very top of the file, I have a global constant, and then I have my main function, and then I have a stack variable, I have a heap variable. And then after I have all of those things, I am going to print the address of the main function, because main is going to live in the code segment. So printing the address of main is going to give me an address that lives in the code segment. And then I have print the value, the address of the global variable to find the read-only constant section. I print the address of my heap variable to find that segment, and then I print the address of the stack variable to find out where my stack actually lives. So, and then the last thing that I do is I actually wait for keyboard input, because what I want to do is I want to be able to have multiple copies of the same program open at the same time, so you can actually see what the addresses of each of these regions of the address space actually are. So let's actually run this program. So I'll start it up in the first tab, and then I'm going to start it up in the second terminal tab here as well. I got a feeling I'm in the wrong directory. Yeah. There we go. Okay, so let's look at this. Now, you might notice that these addresses are very, very large addresses. And that is because this computer here, this is a MacBook Pro, and it has an Intel i9 chip. We have technically 64-bit addressing. Now, interestingly enough, these addresses are actually only 48 bits, because we haven't needed, even though the architecture supports 64-bit addressing, we don't need that yet. I'll explain why in a few minutes. So we're actually only using 48 bits for these addresses. But let's look. Here's the address of main, 1054C0E40. And you'll notice that the address of main for the second tab terminal is in roughly the same area. Not exactly the same area, but approximately. And in fact, if we were to open up more and more tabs, you would actually see they're all, that segment, that region of the address space where the code lives is roughly in the same place for each instance of this process. And we know that each process has its own address space, because that's, what we've been talking about in the last week. Then I look at the address of my global variable, and I see that my global variable because it's a constant, lives very close to the code segment. And that makes sense because the code segment is a read-only section of memory that's globally accessible by the process as threads. And so is the global read-only variable. So it makes sense that it could even be in the same segment, which is what OS 161 does. And then we have the heap address. And we have another heap address. And again, they're very close to each other. And then we have two stack addresses. And again, they're very close to each other. This is kind of weird. So even though I know the processes should have their own address spaces, for some reason, the layout of those address spaces, and it doesn't matter how many of these processes I start up, it looks like the address spaces are colliding in memory. But they're not. It's not even that they're interleaved, like, oh, here's the little bit code segment for this process, and right beside it is the code segment for the next process. No. These addresses that you're seeing here are fake. They're not real. They're not real addresses at all. They're completely fake. And in fact, every address that you have ever seen in 135, in 136, in 241, in 251, if you did any coding in that. We didn't, but maybe you did. I don't know. And 246, they're all fake addresses. No address that you've ever seen has actually been a real address in real physical memory. They're all fake. All of your jump addresses, all of your branch addresses, all of the loads, all of the stores, all of those addresses are fake. Now, that's kind of weird, isn't it? Because how can you load, even the addresses of like the program counter is fake. So the question is, how does anything work if every address is fake? Well, let's go back a bit in time and kind of look at where did this idea of using fake addresses even come from. So I'm going to open up OneNote again. Doesn't matter how many times it updates, it's still broken. And I know I have tried other tools, by the way, and they are broken also, or they're not free, and I like free things. I did, by the way, out of curiosity, I was like, I'm so tired of OneNote being broken. I should do all of this from Windows instead. And that didn't work either because my machine just overheats in Windows. Yeah, I dual booted my Mac with Windows. Why not? All right. So let's look at how programs used to be. So this is our physical memory. That means our actual RAM. And I'd hold up a piece of RAM for you right now, but I actually don't have any on hand. All I got's an SSD and a GPU here. All right, so this is our RAM, our actual RAM. And it is addressed from some start address to some end address. And I'm just going to assume, for the sake of I don't want to write that many hex addresses with that many digits, that we've got 32 bits for addressing here. So 4 gigs of RAM. Okay. Once upon a time, what happened was that we did just use physical addresses. Okay. And what happened when you created a new process, you would go to RAM and you would search to find a contiguous block that would fit the address space of that process. So let's say we wanted to start up, I want to say MATLAB, but it takes more RAM than we currently have on the screen. So let's say you wanted to start up something like Unreal Tournament. And that Unreal Tournament 1 didn't actually take that much RAM. And I know this because I played it on a computer that didn't have much RAM. So here we've got Unreal Tournament, and let's say it takes 128 megabytes. And then when I start up another program, and let's say it needs 2 gigabytes, I'm going to search through here and I'm going to find a contiguous 2 gigabyte chunk, and I'm going to assign it to that program. So let's say that's Chrome. And this is what we used to do. And we would actually give the programs the real physical range of addresses. That I think is 128 megs of addresses. And then for Chrome, we'd give it its real physical addresses. And when you give it the real physical addresses, that actually does simplify things. Because obviously, if you're using fake addresses, there's going to need to be some kind of translation or means to keep track of how do I actually convert this to a real address so the computer can actually find the code and execute the instructions. So when you use physical addresses, you don't have to deal with any of that because you know exactly where everything is. But that's actually the problem with this way of doing things. If I know that Unreal Tournament lives here, then I can look to my left and I can look to my right and I can search for other address spaces because I know where I am in physical memory. Therefore, I know where I am not. And so I can look outside of my range of addresses to try to spy on other programs. It's probably not a good thing. Now, that being said, virtual memory, the concept of virtual memory has actually been around since the 50s, and it's been in use since approximately then to varying degrees. What's really interesting is commercial operating systems, things like Unix and PIC and all of that. They have used full-blown virtual memory for at least 1 or 2 decades more than consumer operating systems have. So things like DOS, which, came out in 1981, it used physical addresses. It didn't use these fake addresses. It didn't hide where the address space was. And it wasn't really considered a security risk because you could really only run one program at a time anyways. So who cares? Why do all this extra translation work when nobody can actually do any concurrency anyways? As they started to let you run more programs, then they reintroduced virtual memory. And the same, by the way, you're thinking, oh, Apple must have done it, though. No. There was no reason to in the early days of consumer operating systems. So this kind of has its origins in commercial ones. So, again, the problem here is that if you know where you live, you know where you don't live, so you can go searching for things elsewhere. There's another problem that we have here as well, and that is when we allocate address spaces in advance and we do this big contiguous allocation, we actually can end up with fragmentation problems, which we're going to be exploring a bit more in a few minutes. The problem is that let's say there was a program living in this tiny region here between Unreal Tournament and Chrome. And let's suppose that there's another tiny region over here, but this area here is full, so this has got something in it. I want to allocate an address space for a new process, but I need a contiguous block, and I have no contiguous blocks free that technically fit the address space, but if I add this one to this one, these two yellow ones together, that would be enough space. So we have this issue of fragmentation. And when you have fragmentation, you either have to solve it or you don't allow the user to open the program because there's insufficient memory. Now, obviously, we'd like to defragment RAM, but that's actually a really costly feature. The other thing that is really problematic with doing this particular implementation of, hey, let's use physical addresses, is what happens if you have less memory than is needed to technically run the program. So if you look at a big program like MATLAB, or maybe you're into video editing, so you're using something like DaVinci Resolve or Adobe Premiere or that one from Avid that I always forget its name, which is ironic because I've used it the most and I still can't remember the name of it. So those kinds of programs need really large address spaces. And it's very plausible that your computer doesn't have enough memory to support that. And yet the program would still run. How is that even possible? Well, it's made possible because we don't use real addresses. And we're letting part of the address space, as a result, not actively live in RAM. Now, why would that even make sense if part of your address space doesn't live in RAM, but you're running the program? Okay, well, let's think of it this way. If you've got a big program like MATLAB, I'm going to use MATLAB as an example because it's huge and it has so many different things in it. When I use MATLAB, I use very, very little of its true functionality. It's got all kinds of tools for simulations. something you may not know that MATLAB has in it, it has the ability to actually spit out an equivalent C program to your MATLAB program so that you can actually run that program from GCC, like compile it with GCC, and run it as a command line C program. But you didn't know it was there. And they've got all kinds of other features, the Symlink Lab and all of this. But when I'm using MATLAB, I tend to be doing something with matrices, or I tend to be plotting some graphs and doing a little bit of curve fitting. So I'm not doing anything kind of crazy. I'm keeping it very, very simple. So if you look at the total amount of the address space, like the code region of the address space that I would actually use, it's just teeny, teeny, tiny. So why keep all of that program code that I'm never going to touch in memory if I'm not going to use it? And similarly, if you look at an operating system, any major operating system, most of the lines of code to an OS are actually for drivers, driver support. So if you look at like the Linux kernel, the drivers that it has are crazy. Like it has drivers for like old CGA screens. It has, which is like 240 by 180 if memory serves me. I haven't used a CGA screen in eons. It's only got like 4 colors, which are black, magenta, white, and cyan. But they've also got like VGA drivers, which is 640 by 480. They've got, and usually 16 colors. They've got drivers for a keyboard layout known as Dvorak, which some of you might use. And I have heard that from an ergonomics perspective, it's actually much more comfortable. It never took off. In the mainstream, QWERTY took off. I did encounter Dvorak when I was a kid, but I didn't know what it was. I was like, why does this program make my keyboard go all funky? And then I realized it was a different key mapping, but I was like, I'm not learning it. So I stopped running the program. It was like a couple days I sat there and I struggled trying to figure it out because I didn't have internet, because it was like maybe 94 or something. Yeah. But the point I'm trying to make is that a lot of operating systems have drivers for things going back 30, 40 years. Nobody has those things, but they still live in there. Why do you want those drivers occupying your physical memory when you're not even going to use them? So one of the things that we have grown into is this concept of not having the whole address space of the program loaded at once. And we're going to talk more about that at the end of the virtual memory segment. We'll actually have a whole kind of episode dedicated to talking about that, because it is what modern operating systems do. Okay. So when we use physical addresses, it's very limiting, and it's not very safe either. So we decided at some point we should abstract the physical addresses because it will help us isolate processes from each other. If each process believes, due to its address space address range, that it is the only address space in existence, then we have effectively isolated it from everybody else. So every process is going to use this range here of virtual addresses. So every process uses the same range, and then we're going to translate that or keep track of where the actual used addresses map in physical memory inside the kernel of the operating system. So each process believes it's the king of the world and it owns all of RAM, even though it doesn't. And you can't go searching for other processes because addresses outside of this virtual range here don't even exist in physical memory. Like it would throw an error. Okay. So that's kind of an overview of where we've come from, how the address spaces are laid out, and why we want to make them fake is isolation, security, and it's going to give us a lot of abilities like having an address space that's larger than the amount of RAM that we actually have, which by the way happens a lot. But what you're more likely to have happen is these days, because of course computers have a lot of RAM these days. My newest machine, which hasn't arrived yet, has 128 gigabytes of RAM, which you're probably like, wow, that's a lot of RAM. And I'm like, that's so not a lot of RAM. I wish I had a terabyte or more. Anyways, you can still run out of RAM, even though one program may not fill that its address space there entirely. And how you run out of RAM these days is by running too many programs. So if you have too many Chrome tabs open, if you decide to open a 4 gigabyte image in Adobe, and then you open another one, yeah, that's going to fill up your RAM. So we have the ability now with virtual memory to actually run more programs than technically their address spaces could fit into physical memory. So let's actually go in now from an overview and actually take a bit of a closer look at what's going on here. So first off, I've already mentioned physical memory. We address physical memory with bits, some number of bits. Now, what's interesting is we do not address each individual bit of memory. And the reason why is because that's too much work. We need extra bits for our addresses, and because addressing bytes makes more sense. So we address bytes, not bits. So we use p bits for addressing, and that gives us access to 2 to the power of p bytes. And remember, that's because this is our addresses. So if for each bit, you have 2 options, a 0 or a 1. So 2 to the power of p, or p bits gives you 2 to the power of p bytes. Now, in OS 161, we use 32-bit physical addresses, so our p value is 32. And that means that we have access to 4 gigabytes of physical memory in total. And if you have a 32-bit processor, that is actually how much memory you have access to. And if you compile a 32-bit program, that is the maximum amount of space your address space is actually allowed to consume, because it will not let you use addresses outside of the 4 gigabyte range. I've learned this the hard way. Thinking to myself, I'll never go outside of the 32-bit range of addresses for this program. And my program did it in the first 2 seconds. Yeah, so I had to make it compile as 64-bit. Back when that wasn't the default. So it is possible, obviously, to use bigger and smaller values of p. So, for example, in the 80s, p was 16. Yep, it was a lot smaller. And in the 90s, it was 32. And now we tend to use 64 or 48. Now, how much memory does that give us access to? How many bytes could we actually address if we used 48? If you use 48 bits to address your physical memory, then you can access 256 terabytes of physical memory. I would like that computer. That sounds very nice. Can you imagine storing everything in RAM instead of having stuff sit on disk? It'd be so much faster. Okay, I'm not drooling over RAM. Anyways, if you have 64 bits, that's even more memory, ridiculous amounts of memory. And I think it is, so if you have 64 bits, that's 18.44 exabytes of physical memory. And if you find a computer that has that much memory, let me know where it is so I can go and ogle it or something. I don't know. Now, in our slides, we're not going to use numbers this big for p, and it's simply because we need a small enough size of physical memory that we can actually fit our example on the slides. So for the purposes of these slides, our p-value is 18, which means we have access to 256 kilobytes of physical memory, which is actually how much memory my first computer had, 256 kilobytes. And it was on a board that was about this big. It was huge. It was so big it actually had to stick out the back of the computer, which is really weird. But I mean, it was supposed to do that. It was designed for that. But yeah, 256 kilobytes RAM. It was a great big board like this. It was huge. All right. So this is our physical memory. So our addresses, or our valid range of addresses, are between 0 and 3FFFF. Remember that we're going to use hexadecimal for addressing memory most of the time. Now, that is how much physical, real-world memory we have. What about how much virtual memory? So how much virtual memory we have is actually decided upon a bit by the architecture and a bit by the operating system. We'll understand the architecture bit in a few minutes, but for now, let's just talk about it from a theoretical perspective. So we are also going to use some number of bits to address our virtual address space. And let's say that's V bits. And again, we do byte-based addressing, so V bits gives us access to 2 to the power V bytes. And in our MIPS system, we've set V to equal to 32. So it's the same number of bits for physical and virtual. This is quite common, actually. This is not unusual. However, in these slides, just to be different, we've decided that our virtual address space will only use 16 bits, which gives us access in our maximum address space size will be 64 kilobytes. Now, just to reiterate, every address that we see in our programs is going to be a virtual address. So your program counter, your stack pointer, your pointers to variables, your jumps, your branches, everything is going to be one of these virtual addresses. And what's really interesting about a virtual address, or the virtual address space, is that a virtual address space can be smaller than physical memory, like we have here in the slides, and that's totally fine. But what's really cool is that you can actually set V to be greater than P and have a virtual address space that's bigger than physical memory. Now, depending on your implementation of virtual memory, that can actually be made to work. And how you make that work is you don't store the whole address space in physical memory at once. You're going to keep it on disk, and then as you need it, you load it into physical memory. So there's some really cool things that you can do there. So please excuse the label in the center of this block here. It's supposed to be deleted. So we have 2 address spaces here. So we've got process A. Now, the size of virtual memory is not the size of the address space. A process does not have to use the entire amount of virtual memory for its address space. It can use a smaller region if it wants to, or it can use the whole region. It's really up to how is virtual memory implemented and what is the process actually doing. So in our first example, we have processes A and B that are using less than the total amount of virtual memory available. So A is going to use 28 kilobytes of the 64, and B is going to use 48 of the 64. Okay? That's not too bad. Keep that in mind as we go into how this all works. So as I've said before, but just to reiterate, we are doing this virtual memory stuff to isolate processes from each other, but we also do it to isolate processes from the kernel. Because I don't want one program to be able to access the memory of another program, I really don't want like Minecraft to be able to access my kernel. That would be really bad. So we're going to use these fake addresses as a form of isolation. Now, when we're actually talking about virtual memory, we have 3 big goals that we want to have. We really want, and I don't have it on the slide here. I should really add this to the slides. What we really want for our virtual memory implementation is transparency. That is, the user programs should never be aware that the addresses it's using aren't real. It shouldn't ever be aware. The other thing is efficiency. Because we are using fake addresses and our CPU doesn't know what a fake address is, we obviously need to translate from a fake address to a real address before we actually do any computation. We need to make sure that that translation happens efficiently. That is, the computation of how you go from fake to real needs to be really, really fast and easy. And the amount of extra memory we use to perform that translation needs to be as small as possible. So we are looking at efficiency. And the third thing that we do as a goal is protection. It means the method we are using to implement virtual memory should actually, provide the isolation that we want. All right. So, and the other things, just to reiterate, is that you can have a virtual memory size that is larger than physical memory. That's totally fine. But you can also have one that's smaller. And the total size of all of the virtual memories for each process can actually be larger than physical memory. And that's going to give us a greater support for multiprocessing if we do it actually properly with on-demand paging, which we'll talk about on our last day of virtual memory. All right. So we know then that every virtual address is fake, and we're going to need to translate it to a physical address. Because if I try to have the CPU load an instruction from address 10, if that is a fake address, that's a virtual address, then address 10 may not actually contain the instruction I'm trying to load and execute. So before the CPU actually tries to execute an instruction or load an instruction, it needs to have the addresses translated from virtual to real. Now, how are we going to do that? One way that we could do it is that we could throw an exception for each instruction and have the kernel of the operating system do the lookup. So there'll be some kind of table or mechanism by which the kernel will know how to translate the virtual addresses to real addresses. You saw how slow system calls were. Look at all the work we had to do. Switching the CPU into an unprivileged state. And then, of course, we had to do things like save the trap frame, figure out what the exception type was, do the work, and then return all of that. You don't want to be doing that for every instruction of your program. And to say it's every instruction, you would actually have to do it multiple times potentially, up to 3 times per instruction, because you'd have to load the program, you'd have to translate the program counter. If you had to load something from an address, you'd have to translate that address. So you could have multiple translations per line of assembly. We don't want to throw 3 exceptions per line of assembly. That's insane. We'll never actually get any real work done. So what we really want to happen is we want the hardware to be able to perform the translations. Things that happen in hardware are generally speaking faster than things happening in software. And something you might remember from CS350 is you actually have a piece of hardware on your CPU that's capable of doing this. It's called the MMU, or Memory Management Unit. And its job is to take an address and translate it from virtual to real. And then it can give it back to the CPU, and the CPU can go about its business. And in fact, we can put that in the pipeline in advance. Well, it would have to go in advance of the pipeline so that the CPU never even encounters this. Now, what's interesting about this is there are different implementations of the MMU. They are physical hardware. And each MMU is going to support a different translation scheme. And those translation schemes that your MMU support is kind of going to dictate to your operating system what's the maximum virtual memory size, because it's going to dictate how many bits you're allowed to use. But it's also going to dictate what are the possible translation schemes that we will permit, because the hardware is dictating to the operating system how it's going to do its translations. And so then the operating system has to be tied to has to know the architecture it's going to run on so that it can actually do the address spaces set up correctly and make sure the MMU is updated with the correct values. So let's look at the simplest mechanism for doing address translation, and that's known as dynamic relocation. And in terms of the 3 goals of transparency, efficiency, and protection, dynamic relocation knocks them out of the park. It guarantees transparency. It is the most efficient in terms of computation time and computation space, and it definitely offers isolation, protection. So let's see how it works, and it's very simple. We are going to assume that address spaces are contiguous blocks of virtual memory. So in this case, again, process A uses 28 kilobytes and process B uses 48 kilobytes. We are going to look in physical memory for a contiguous block of space that fits each of those address spaces, and we are just going to map that block to it. So the 28 kilobytes of process A get mapped here, starting at address 24,000. And that is going to be process A's address space in real physical memory. And then process B's 48 kilobytes, we found a contiguous block over here starting at 13,000. Now, to make sure that we can translate from A virtual to A physical, we're going to keep track of 2 values for the process: the offset and the limit. The offset is where in physical memory does that address space actually start. So in this case, A starts at 24,000. The limit is the length of that address space. It is not the length of virtual memory, because the length of virtual memory is technically 64. It's the length of the region you're actually using, which in this case is 28 kilobytes. So we're going to have the 28 kilobytes here as our limit. For process B, its offset is 13,000 and its limit is 48 kilobytes. So for each process, we are going to need to store only two integer values, the offset and the limit. And then the MMU translation is very, very simple. So first off, the MMU will have two registers. They are on board the MMU, and the one register is going to store the offset for this process, and the second register is going to store the limit for this process. And then what happens is when the MMU receives an address, it is going to check if the virtual address is less than the limit. If it's less than the limit, then it lives in the address space of that process, and therefore it's valid and can be translated. And so all we have to do the translation is add the virtual address to the offset or relocation value, and you're done. If, however, the virtual address is greater than or equal to the limit, we throw an exception. It is not a valid address, and we would be attempting to access memory outside of our process's area, and that's very bad, so we throw an exception, and the operating system should terminate the program with a segmentation fault. Yeah. Now, some people always ask me every term, why is it less than L? Why isn't it equal to L to be valid? And the reason is simple. We start addressing things at 0. So if you have an array that has 10 elements in it, array at index 10 is not actually in that array, but 0 through 9 are. So it's less than L to be valid. Now, what's interesting about this is each time that you do a context switch between threads of different processes, the operating system is responsible for updating the MMU with the new relocation and limit values for that process. So the operating system is still involved, but only under context switches or when exceptions are thrown, because the operating system is going to actually handle what happens if the user program tries to do something bad, like accessing an address outside of its range. So let's do some little translations here, just some sample ones. Not too hard. That. So I'm only going to do process A for you. I'm going to let you do process B on your own. There we go. So my computer's bogged down. Anyways, so let's look at this. Let's get an actual pen going here. We have for process A, we have a virtual address 0x102c. And we want to know what is the physical address. So first thing we're going to do is we're going to pretend we are the MMU, and we are going to compare V to L, which is in our limit register. And I want to know, is 102C less than 7,000? Obviously it is, so it means it's a valid address. And then to perform the translation, we are simply going to add V to the contents of the relocation register, which of course gives us 2502C. And you're done. Isn't that so efficient? All you had to do was check and add. Very simple. And then we will move on to the next address, which is 8,000. We compare it to the limit and see clearly it's bigger than 7,000. So we are being pretend MMU, so the correct answer here is to say exception. It is not a valid address, and if you encounter something that is not a valid address, you write exception. And then the last address here is 000. That, of course, is less than 7,000. And when we add it to our relocation register, we get that. Now, to prove to you that this is isolating process address spaces from each other, I'm going to translate 102C for process B. So for process B, the same virtual address of 102C is going to translate to 1402C. And you can see here that the same virtual address is translating to two very different physical addresses. And this is how the isolation is actually working. It's because even though the virtual addresses are the same, the relocation and limits are different. And so these map to different regions of physical memory. So I'll let you finish up those translations there. Okay. Now, if this is so efficient and it works and it's transparent and it isolates, why do we have like 3 or 4 lectures dedicated to virtual memory? Because it has a problem. The biggest problem with dynamic relocation is that it suffers from fragmentation. Now, in the address spaces that you've seen here, where we don't have separated code, data, and stack segments, where it's all squishy together, and each address space has a different size, we end up with something called external fragmentation, which is where we need a contiguous block of physical memory to fit the new address space, but one doesn't exist. So it's externally fragmented. However, if we look at how real address spaces are laid out, we note that due to the layout, they're all technically the same size. So the code segment in OS 161 always starts at this address here. And the data segment in OS 161 always starts at this address here. And the stack segment in OS 161 always is here. Always, always, always. Which means that regardless of how much memory we actually are using for dynamic relocation, which requires a contiguous block of addresses, every process would require 2 gigabytes. And what we end up here is not with external fragmentation, because you don't get external fragmentation when every allocation is the same size. You get internal fragmentation here because there are large blocks of memory that are allocated and assigned to the process, but not actually usable. So dynamic relocation suffers from fragmentation. And this is a problem because you're either going to have to deal with the fragmentation externally and defragging it, or you're not going to be able to run that many processes at the same time because each one is so huge. So while this is a super efficient implementation, it's not practical in any way. Now, a couple more things that I want to say about this. You may have noticed when I had these terminals open that the code segment for the same program is in a different spot between these two. And if you were to run this program on Windows or run this program on Linux, you would find that the same thing is true. You would find that the code segment lives at a different address despite it being the same program. And the reason is that modern operating systems do this thing called address space layout randomization. And that means that the code segment, while it will live in a certain range of addresses, the exact starting point is randomized. And this is an additional security feature, apparently. Now, OS 161 is not so concerned about security, so our code segment for every process lives at the exact same address. Yeah, fun stuff, right? Okay. One other thing then we want to say. And that is, let's go back to the slides here. You might be wondering, I have always been told that the stack lives at the highest addresses, at the complete end of the address range. That's a lie. It doesn't live there. And in fact, in every operating system that you use, it actually is in the middle. Yeah, there's a reason for this. We will get into this in greater detail, but essentially, because we also want the kernel to use virtual addresses, we split the virtual address range into two. One half is going to be for the user and one half is going to be for the kernel. And so the stack lives at the very top of the user range, and then everything beyond the stack, so addresses higher than the stack, are going to be for the kernel only. And again, we will talk about that later. All right. Just a quick question for anyone on Twitch there. If you're finding the audio and video to be out of sync, please let me know. I've noticed there was a comment on Piazza the other day about there, maybe it was YouTube about that. And I know my computer is bogging down a little bit, which does tend to do that. But if they're out of sync, do let me know. All right. Looking at how a real address space looks like, we want to try to solve some of the problems of dynamic relocation. In particular, why on earth, if this is what my address space looks like, why would I allocate 2 gigabytes for this when I'm only using 1.2 megs of it in total? Okay. Well, could we do something different? Couldn't we just use or allocate stuff for these individual segments? So what if I just tracked the code segment? What if I just tracked the data segment? And what if I just tracked the growth or the stack segment? You know, there's something I can do to help here. It's probably Chrome. So that should help things out a little bit. There we go. Hopefully that will improve things a bit. All right. So, that's not what I was looking at. What I want to do is, instead of tracking the entire address space, I just want to track the regions that I'm actively using. So the code, the data, and the stack segment. This is actually a different form of virtual memory called segmentation. And this one has actually been used for many, many years. And in fact, it was used by Windows in the early days because it's easy and it's efficient and it's transparent and it offers isolation. So the idea is that instead of mapping the entire address space to a single contiguous block, we're going to map only the regions of the address space we are using to contiguous blocks. So we'll map the code segment to a contiguous block in the physical memory. We'll map the data segment to a contiguous block in physical memory. And we'll map the stack segment to a contiguous block in physical memory. And so for each segment, we need to keep a segment relocation and a segment limit. Now, in order then to do the translation, I need to know which relocation and which limit I need to use in order to perform the translation, which means I need some kind of segment identification. And so what we're going to do is we're going to subdivide the virtual address into 2 ranges. The upper K bits are used to identify the segment, and the lower V minus K bits are going to be the address within this segment. So the number of segments is actually going to restrict the maximum size of the segment, because if you need 2 bits for the segment number, then you only have 30 bits for the actual segment address. And then what's going to happen here is your MMU is going to extract the bits for the segment number, and then it's going to use the segment number to decide which of the relocation and limits it needs to use to perform the translation. Now, what's interesting about this is while it does completely solve internal fragmentation, it actually didn't solve our external fragmentation problem, because now every allocation, while it contains no wasted space, each allocation is now of a completely different size. So that's a problem. But this method actually still works pretty well. And I mean, it worked well enough that, like, I'm pretty sure Windows 3.1 actually used this technique, and several other operating systems. So let's look at it a little more closely. So you've got 2 regions in these address spaces, segment 0 and segment 1. Since we only have 2 segments, that means we only need 1 bit to identify the segment number, because 0 will be segment 0, and if the bit is 1, it's going to be segment 1. So I'm going to map segment 0 of process A to over here. So here's its offset and limit. And then segment 1 of process A, I'm going to put it here, and here's its offset and limit. And then segment 0 of process B gets here, and segment 1 of process B goes here. So that's pretty cool, right? So for each segment, I need an offset and a limit. Now you might be like, well, that's taking up some extra space. Yes, it does take a little extra space. However, here's the thing. How many segments does an address space realistically have? Does it have 5 or 6? Even if it has 5 or 6, that means you're storing per process 12 integers. And if you've got, 32 gigs of RAM or 64 gigs of RAM or 128 gigs of RAM, do you honestly care if each process is storing 12 extra integers? You don't. So this is still, in terms of how much extra space we need, it's very, very efficient. And the computation of the address is also very efficient. And there are 2 approaches to doing the translations. Well, there's more than 2, but here's 2 of the big ones. The first one is the MMU actually has relocation registers and limit registers for each segment. So the MMU is going to dictate exactly how many segments we are allowed to have in our address space. And because it's going to specifically have that many registers for each. So we have one register, so we've got a relocation and limit for each segment. And what the MMU is going to do, it's going to get the segment number from the address. And it's going to get the segment address, so the address within the segment. So it's going to split the virtual address into 2 parts. We're going to use the segment number to identify which relocation and limit register we need. And then we are going to compare the address within the segment to the limit for that segment. And if it's greater than or equal to, we throw an exception because it's an invalid address. If, however, it is a valid address, that is, A is less than the limit for that segment, then we are simply going to add A, which is the address within the segment, to the relocation for that segment, and we're done. So it's pretty much the same math as dynamic relocation, but now we just need to identify which region is it. You're done. It's so simple. Now, why don't people use this one? So this method is very simple, having the register on the MMU. But the problem here is that not every segment is going to be read-write. And we want the MMU to throw exceptions if we are trying to write to a read-only segment. So in order to support that, we would actually need a third register. Here's the thing. Registers consume physical space on the MMU. We want the MMU to be as physically small on the CPU as possible. So this one actually ends up with a fairly big MMU. It also is going to dictate to the operating system the layout of the address space, and we may not want that. I don't know about you, but I don't like people telling me how I have to do things. A more modern approach is the MMU contains only 2 registers. The first register tells us how many segments there are in the address space, and the second register tells us the address of what's known as the segment table in memory. And then what happens is the MMU still splits the address into 2 parts. We get the segment number and the segment offset. If the segment number is not corresponding to a valid segment, we throw an exception. And then if it does correspond to a valid address, we use the segment number to look up the entry in the segment table, and the entry in the segment table will give me the limit and the relocation and bits about is this read-only or not. So all of that information will be stored in memory. Now this is a little slower because it's not on the MMU. You actually have to leave the MMU and go to physical memory for this, or have a cache, which MMUs have a cache, let's be honest, but we'll talk about them another day. So this is a little slower, but it's more flexible in the fact that the MMU is A, smaller, and B, if the operating system wants to use segmentation but with fewer segments, it can. So there will be a maximum number of segments the MMU supports, but you don't have to use all of them. You can use fewer if you want. And in fact, you could have every process uses a different number. So that's kind of cool. So we're going to do a lookup, and then we'll do the exact same math as before. So that's pretty cool. So let's do a few translations here. And again, I'm just going to do process A. I'm going to let you do process B on your own. So we're going to, we see that our process A has 2 and B both have 2 segments. So we know that the segment number uses a single bit. the bit is always the highest order. So I'm going to make a table here. So here's, oh, I don't want to write with a highlighter. That's very silly. Here's our virtual addresses. And I'm going to calculate the segment number and the segment offset and then the physical address. So our virtual address is 01240. And I want to know, what is the segment number here? And a lot of people, the first time they see segmentation, they're going to be like, oh, the segment number is 0x1. But it's not. It's absolutely not. And the reason why it's not is because this is written in hex. And we're not asking you for the highest order hex digit. We're asking you for the highest order binary bit. This is actually 0, 0, 0, 1, 0, 0, 1, 0. That is the address in binary, and we want the highest order bit. The highest order bit is this 0. So the segment number for this one is 0. Which means the segment number, or the segment offset, is the remaining bits. And luckily, that actually translates right back to 1240. Now, I compare it now to do the translation. I compare that to the limit. It's within the limit for segment 0, so I'm going to add the relocation to it. So I get 39240. Okay? Now, looking at the next address, actually, I think I'm just going to do the next address, and I will let you do the other ones on your own. If we look at A0, we have to, again, split it into the binary here, and we end up with this address is 1010. And in this case, our highest order bit is 1. So I know that this is in segment 1. And to get, if I want to turn this into the segment offset, I'm going to set all of the segment bits to 0 because it's what's left. And so our offset is 20A0. And I compare that to my limit register for segment 1. It is bigger than the limit, and so this one, or actually, never mind. I thought it's smaller than the limit. My apologies. And so I'm going to add this to the relocation register. There we go. So there are our two addresses. Now I'm going to let you do the rest of them to get some experience. Remember that if it is not a valid address, we write exception. And as proof that you are actually getting isolation, make sure you do process B as well with the same addresses. Now, what we're going to do in our next episode is we're going to look at how can we get rid of the external fragmentation. We get the external fragmentation because each allocation is of a different size. So what I want to do is I want to kind of extend the idea of segmentation, but make it so every allocation is the same size. And how we're going to do that is with paging. So in our next episode, we are going to talk about paging, which I'm sure you might remember from CS350. So we will see you next week. I hope you all have a lovely weekend.